Hello, today we're going to be working with imaginary numbers. Before we do that, I want to kind of review a couple of things about just regular terms that we need to know. First off, when we are looking at combining like terms or multiplying terms, anything like that, we want to make sure that we're understanding it correctly. So anytime we're adding terms together, they have to be like terms. So I can't add a 4x and a 2x squared because they're not the same kind of terms. Here we're multiplying, but when we have a 3x plus 4x, that just becomes 7x because those are like terms. Now, when we're multiplying, we have 3x times 4x. The 3 and the 4 get multiplied to give us 12. The x and the x multiply together to give us x squared. We don't have to have like terms to multiply and divide. We do have to have like terms to add and subtract. And this is very much a review. It'll make a little bit more sense later. On the next one, 2x squared times 4x. We've got 2 times 4 gives us 8. X squared times x. If we have x squared, that's x times another x. So that's, whoops, I'm not sure what sign I was trying to make there. That's the x squared. So if we have x squared times x, that gives us x to the third. So that one's going to be 8x to the third. The next one, if you'll notice here, we're just adding, so it's actually unnecessary to have these parentheses. So this can just be 2x plus 1 plus x plus 5, and then we combine our like terms. 2x plus x gives us 3x. 1 plus 5 gives us 6. So 3x plus 6. On the next one, however, we have a minus. So we're subtracting this whole second set of parentheses, which means we kind of need to distribute that negative into the second set of parentheses. So we're going to go minus x and minus 5. So this would be 2x plus 1 minus x minus 5. A lot of people tend to think a negative out in front of parentheses makes everything negative. What it really does is makes it the opposite of what it was. So if it was positive, it's now negative. If it was negative, it's now positive. So we're going to combine our like terms, 2x and negative x. So 2x minus x is just x. 1 minus 5 is negative 4, so x minus 4. So when we're dealing with imaginary numbers, a lot of this is some review stuff that I want you to be able to do and understand. So I'm going to run through these real quick. First off are all of our squares, perfect squares. Negative 4 squared is 16. Negative 3 squared is positive 9. And so on and so forth. So there are our most commonly known perfect squares, 0 to 12. Notice that our negative numbered squares are also positive because anytime you multiply a negative by itself, you get a positive. And that kind of brings us to square roots of negative numbers, and we're not quite there yet. This is more just simplifying square roots. So when we are simplifying square roots, I'm going to rewrite that and just say that's not quite the title I want to go with. Simplifying square roots. What we're trying to do is get as much out of the square root sign as we can. And what we do is we split that square root. So this one right here, we've got square root of 32. We can split that into 16 times 2. Split those apart. Take the square root of 16 to give us positive 4. So we got as much out of there as we can as a whole number. So we don't want to put this in the calculator and get our decimal approximations. What we want to do is split it up. And there's a lot of ways to do this, and some people can do them really fast because they know a whole bunch of stuff off the top of their head, and some people can't. So it's always a good idea to factor if you're not sure. So 1 and 27. Set 27 is not divisible by 2. 27 divided by 3 is 9. And there we can stop, because what's going to happen as we go down here, there's no more factors of 27. But what will happen is these numbers will get smaller and smaller and smaller, and these numbers will get larger and larger, and they'll get closer to each other. So as soon as we hit a perfect square on the right side in this method of factoring, that's the one we want to use. So I can rewrite this as the square root of 9 times 3, which means it's the square root of 9 times the square root of 3. The only reason I put this perfect square first is because it turns out nicer in the end. Then I take the square root of 9 to get a 3, but the square root of 3, this one, that's not a whole number, so I'm going to leave it. We need to think of that as getting absolutely perfect to get out of that little jail that is the square root sign. So next, 48. We got 1 and 48, 2 and 24, 3 and 16. And now we can stop because we have a perfect square. If we continue on, those numbers are just going to get smaller. So we have square root of 16, square root of 3. So this ends up being 4 square root of 3. 18, 1 and 18, 2 and 9, and we can stop there because of that 9. That's why it's good to have these numbers kind of at the top of your head when you're doing this, so you kind of know those. So square root of 9, square root of 2, gives you 3 square root of 2. 150, 1 and 150, 2 and 75, 3 and 50, not divisible by 4, 5 and 30, 6 and 25. And 25 is a perfect square. So we do square root of 25, square root of 6, and that gives us 5 square root of 6. 6 can be split into square root of 2, square root of 3, but that doesn't really help us any, so we're just going to go ahead and leave it like that. So that's simplifying square roots, something that I want you to be familiar with so that we can talk about how we split that in imaginary numbers. So now we have, we know we can't take the square root of a negative number. So mathematicians created the imaginary number I. So I is a complex number such that I squared equals -1. We often think of it as the square root of -1. So this right here would be an important thing to write down in your notes. If it were me, that's what I would do. So we can split off these. When we have a negative, we have to take that -1 away from our square root so that we can take the square root of 9 and write it as 3. And then we rewrite the square root of -1 as I. So if we look at the square root of -25, that can be written as the square root of -25 can be written as the square root of 25 times the square root of -1. So that gives us 5 for the square root of 25. And then instead of the square root of -1, we write I. Same thing for the next few. Split them up, so 6I. Here, let's just drop down this 10 and deal with the -16. So that's going to be the positive square root of positive 16, square root of -1. So 10, and then the square root of 16 is 4, and then I, so that's going to give us 40I. And square root of 144 times the square root of -1, 12I. So basically, all of these, what this kind of brings up a point of when we're working with I, we treat it very much like we would a variable until we end up squaring it, and then we need to replace it with -1. So if we look at some of this arithmetic with it, 2I plus 4I, just like 2x plus 4x, is going to be 6I. 5 times 3I is just going to be 15I. -4 times 2I is going to be -8I. 3I minus 9I is -6I. 2 plus 3I plus 8 plus 4I, those parentheses are not necessary because this is being added. So we add the 2 and the 8 to get 10. 3I plus 4I is 7I. And here we're going to distribute that negative just like we did in that kind of warm-up. So we've got 5 plus 7I minus 9 minus 5I. 5 plus negative 9 is going to be negative 4. And 7i minus 5i is going to be positive 2i. So then when we're multiplying and we have powers of I, that's when we have to start paying attention, because we have this I squared equals negative 1. It's very important that we note that. So we have 2i times 5i, that's going to be 10 from the 2 and the 5. Whoops. From the 2 and, oh, no, keep pushing the wrong things. What did I just do? Ugh, too much. Okay. So I have the 5 and the 2 for the 10, and then I times I, which is going to give me I squared. And I've squared I, so I need to go 10 times negative 1, and that's going to give me negative 10. 3i squared, this whole thing is being squared, so I'm going to square that 3 to get 9, and then I squared. So I have 9 times negative 1, which is negative 9. Negative 6 times 4, negative 6i times 4i. Negative 6 times 4 is negative 24. I times I is I squared. So negative 24 times negative 1 is a positive 24. And this one threw people a little bit. The 5i squared is all in parentheses, so I'm going to leave that for now. But this whole thing is being squared. So negative 4 squared is going to be positive 16. And then I have I squared. So I'm going to go ahead and put what I know here, 5, and I'm going to replace the I squareds with negative 1. So I have, if I just multiply that straight across, I'm multiplying two negatives, which is going to give me a positive, and they're both 1. So 5 times negative 1 times 16 times negative 1 is really just going to be 5 times 16. So 5 times 16 is going to give me 80. Double check my math there. Yes, that's correct. Okay. I didn't have a calculator on me, so. All right, moving on with complex numbers. Those are going to have that form A plus BI, the sum of a real number and an imaginary number. So 3i is 0 plus 3i. We're going to work with complex roots. Whoops. Next class, shrink that down a little bit. But we're going to look at what happens when we multiply a pair of complex conjugates. So the A plus BI and A minus BI. So we're going to take the 4 plus I, put that on the outside, 4 minus I, put that on the outside, and we're going to multiply. So we got 4 times 4 is 16, 4 times I is 4i, 4 times negative I is negative 4i. Negative I times I is going to give me negative I squared. And then I'm going to rewrite that as negative, and then the I squared is negative 1. You got to be really careful with negatives. So that ends up being a positive 1. The 4i and the negative 4i add out to 0. So what I'm left with here, I just wrote 2. It shouldn't have been 2. Sorry if that was confusing a moment ago. Plus 1. So this is really, when I take this, this is 16 plus 1 is going to give me 17. All right, 5 minus 3i, 5 plus 3i, 25, negative 15i, positive 15i, and then negative 9i squared. So this negative 9i squared is going to give me negative 9 times negative 1, which is a positive 9. The 15 and negative 15i's, those are going to add out. So I've got 25 plus 9, which is going to give me 24. So basically what happens when we do this is we're multiplying the first ones for that first term, a squared here, and then negative bi plus bi, sorry, I had that opposite, is really just going to end up squaring that b. So this is going to be a squared plus b squared. Finally, rationalizing the denominator. This is one of those things that I don't know if it's probably not relevant at all anymore, but in many circles, we don't want to have a square root in the denominator, so we rationalize it. We rationalize it by multiplying by 1. Anytime you divide something by itself, you're multiplying by, it's 1. So when we multiply by 1, that can take on many forms. So if we're trying to get rid of a square root of 3, we multiply by the square root of 3 over the square root of 3. Multiply across the top, so 1 times square root of 3 is square root of 3. Square root of 3 times the square root of 3 is the square root of 3 squared. And the square, as you guys know, and the square root are inverse operations, so those two cancel each other out and we're left with 3. So perfectly fine to have a square root in the numerator, not to have it in the denominator. So because I is the square root of -1, we also don't want to have it in the denominator. So we're going to multiply by 1 by doing I divided by I. And we could do 3i. A lot of people did the first time. It just takes more to reduce from there. So across the top, I've got 1 times I, which is just I. And then I've got 3i times I, which is going to be 3i squared. So I on the top. On the bottom, I have 3 times -1. So this is going to be negative I over 3. You can put that negative with the 3 if you want. You just need to only write it once. So that's what we need to know about working with imaginary numbers. And really, it's just you're going to treat it mostly like a variable like you would any other time, except for when you square it or when it's in the denominator. And that's it for today.